All right, so eddy currents, as I said earlier, they're currents flowing in loops. And what exactly causes them? What causes those eddy currents? The change of magnetic field. All right, so if you have a solid material that is subject to a changing magnetic field, that solid material will develop some currents internally, and those currents are induced currents, which according to Lenz's law flows in a direction to oppose the cause, whatever is producing it. So those eddy currents are going to be flowing, and it will oppose the cause, which means it will try to weaken the change of flux. That's one problem with that. And the other thing is those eddy currents are so strong because they're just flowing in a material with almost very little resistance, and so those currents are pretty high, and it will produce unwanted heating effect. You don't want them. So all these are basically going to be loss of energy. So eddy currents are basically something that we don't want, but at some places we definitely need those eddy currents. Yeah.
Can you show us this pendulum?
The pendulum part of it?
Yeah, like with your actual pendulum.
With the real pendulum?
Yeah.
I don't have one.
Oh.
With a normal pendulum? I don't think a normal pendulum will work properly, because with a normal pendulum, it's just a small object, and we should have a very strong magnetic field as well, too. But it will show some definitely difference. It will not oscillate as much as it's supposed to be. Well, let me see. I will see if I can practically set one up. It should not be difficult. It should not be difficult. I should be able to set one up, at least by using a normal magnet, But an electromagnet will be much better. If it is an electromagnet, it will work much better. But I can try setting up one like that. There are some ready-made demonstration kits also coming up with that. So circulatory, like the currents that are flowing in the material is what causes eddy currents. And how are eddy currents removed? So remember I told you about this pendulum with the sheet metal? If it is basically a solid sheet of metal, you will have circulatory currents going like that all around, and those circulatory currents are going to be flowing in such a direction to oppose the cause. So this pendulum thing will, the oscillations can be suppressed very quickly. And now how do you not let it undergo the suppression? Is by slicing it as if you're slicing bread. So basically all these are cuts. And when you have cuts like them, you cannot have large-scale currents flowing through them. You can have small currents internally, but they will not cause as much damage as the bigger one, right? And so this is one way of reducing eddy current effect. You cannot get rid of eddy currents completely. Completely not possible. You can minimize it a lot by using this so-called lamination. By laminating the material, you can get eddy currents minimized to a good extent. That being said, that is one of the losses that you cannot completely avoid. So if you have a motor, for example, the motor has a core, right? And that core will be subjected to changing flux. And when the core is subject to changing flux, it's going to have eddy currents. How can you minimize eddy currents? Laminate it. But how much can you laminate? There are limitations to the lamination itself. And when you laminate it, you can cut down the losses a lot, but still you can't rule it out. So that loss is something that is always there. Loss is always going to be there. Now, in a moving coil meter, the magnets, those are the magnets. And in the middle is a core, a cylindrical core. That's a 3D version of it. Right? So that's a cylindrical core, and the coil is wound on the core. the coil is wound on the core like that. Make sense? The coil goes on the core. So if that's a core, wow. If that's a core, the coil is going to go around like that. Okay? So that is a moving coil meter, and then we have the pointer. That's a moving coil meter, and that's a pointer. So if I can pass this around, and if you look inside here, you'll actually see the core. And this core is a solid core. It's not laminated. Deliberately, it's not laminated. So what's the purpose of the core? Number one purpose, someone said it here, is to provide mechanical strength or stability. So the coil, instead of winding the coil in the air, it is better to wind it on something solid, so you'll have more inertia and more strength, right? That's one purpose. The second purpose is to strengthen the magnetic field. To strengthen the magnetic field strength inside here, because this is a ferromagnetic material, you want more magnetic field inside the coil. So we want to strengthen the magnetic field. That's the second objective. The third reason as to why this is sitting here is to provide critical damping, something that you've seen before, last year. Critical damping is not letting this pointer oscillate on both sides of the real current value and then swing forever and finally lose its energy and come to rest. You don't want that, because as soon as you connect something and you want to read the current, you look and it should be ready for you. You don't want the pointer to go, you don't want the pointer to be swinging like that and then waiting to come to a halt. So even if I do this, see how quickly it's come to a halt. Why is it coming quickly to a halt? Is because this core, when the core moves in the magnetic field, what is being set up in the core? Eddy current. So eddy currents inside here flow in such a direction to oppose the cause. So if the pointer is trying to go that way, the eddy currents are trying to prevent its movement. And if it swings too far, then it is going to come back, and when it comes back, opposition. So opposition all the time is what suppresses the oscillations like that. See? When you connect it, it go like, that's it, over. Your speedometers, any dials that you have, they're all like spring mounted actually, but see the way they kind of quickly come to a halt somewhere, not oscillating. Imagine you have a speedometer, you have your car dashboard and all those pointers are kind of dancing like that, because they're not coming to a halt quickly. It'll look awkward because you can't read one of them properly. Your RPM meter is like dancing like that. No, we don't want it. We want to like go there, stop, go here, stop. And that is critical damping achieved by. So here we are deliberately keeping it as a solid core, not laminating it, because we want eddy currents to help us. But here in a motor, we don't want the eddy currents, and so we laminate it. So wherever we don't want the eddy currents, we laminate it. The same way as a transformer core. Did I say about the transformers? Yeah. So in a transformer core, I think I passed this around. So in a transformer core, these are laminations. You can see all these sheets are separated. At the same time, they're put together with a little bit of varnish in between. And therefore, electrically, there is no contact, but magnetically, there is full contact. Okay? So it prevents the circulatory currents, the eddy currents. And thereby what will happen, the benefit is there is hardly any loss here. So when I use a transformer, this will not get heated up. Now instead of this laminated core, if I use a solid core and connect it, what will be seen is this thing becomes really, really hot because of the eddy currents. And that will remove the efficiency. So if you're going to take 100 watts from there, out of 100 watts, 95 watts will be gone as eddy current losses here as heat, and only a little bit can be used later. Motors, the same thing. Look at this. These are coils. These are the coils that are producing magnetic fields, and the motor itself you can see the windings of the motor from inside. I'll pass this around. So you can see the windings of the motor from the inside, and you can see the coils that are supposed to be producing the magnetic field, right? Right? Okay. And so this core is an essential part. There are two cores here. One is this one, which produces the magnetic field, and there is a core on which the wires are wound. It's hard to see it. Only when you take this out, you will be able to see it. Okay, so the core, the winding is done on a core, but this core is different. But you can see they're all laminated. They're all laminated because you don't want eddy current losses in them. Okay, so I'll pass this around and you can have a look at it. Have you seen this?
I wouldn't hurt to look at it again.
Okay, you can just look at it again. I'll pass it from both directions. Look at this. And you may have to look at it later on again to search for something else. But right now, this one will be just to check the code. Just to look for this thing. You see it?
So that coil won't have lamination?
Say it again?
That will not have any lamination?
No. That we don't want lamination because we want the critical damping. Whereas in that one, we need that lamination because eddy current is something that can resist the motor. So if you have a motor with just solid core, the purpose of the motor is basically to spin, right? Now, the very spinning action produces eddy currents, which will be counteracted. So therefore, it will not spin as fast. So you need to, if something is spinning in a magnetic field, you need to make it spin freely without the eddy current effects. So you can see the laminations, how it is done. Okay. So the purpose of lamination is to reduce the eddy currents. Now before you go take a test on these concepts, see, not everything in chapter 21 is required for you, and therefore whatever is covered is what you should focus on. But then, unlike every other time, can you please go to your e-textbook, look at the questions there, practice it well, then go for the test. Right? You don't do it normally, but most of the questions that you're actually going to see on 21 test, they're all here. So why don't you just check what variety of questions are there, and then learn how to do it, learn the concept behind it, and after that you'll be good. All right. Now moving on to transformer itself. Let me give you the ideas of transformers and the equation for the transformer. Okay. Now, a transformer construction can be different types. You can have transformers if you take a bunch of wires like this, and then one set of wires wound on it, you can connect it to a power, and then another set of wires from here. This is a transformer. If you take any bunch of, like a core, basically a core or a solid core, and then wind these wires like that, this is a transformer. That is but the problem with this transformer is the magnetic flux which is produced in the core is lost. See, it's kind of lost like that. And this side is also open. So this won't be a very efficient transformer because we are having magnetic losses. Now, if you don't want the magnetic loss, we want to trap the trap everything inside, then this is one thing you can do. You can do this kind, like that, and then wind it over here. This is one winding called the primary, and this is the other winding called the secondary. So that's a secondary winding here, and that's a primary winding. This can be done. Now what happens is the flux is going to go like this and then link it like that. So the flux is going to be going along in this direction. So the flux is changing in this way. All right? That's another way of doing it. Over here, the magnetic losses are minimized much more because whatever flux this is producing is running through this and then going into the next coil. So not much of loss is taking place. But the distancing is actually something that we definitely don't want to do. Like, although I said the losses are minimal, still it may not be 100% efficient. We have transformers that are of this type also. What will happen if I connect a supply here? What will happen when I connect a supply there? How many volts will be seen over here? Like suppose I connect 6 volts here. What can you expect on the secondary? If I connect a voltmeter here, what will this voltmeter do? Will it read anything or not, is my question. Remember how I explained Faraday's experiment itself? Yeah.
Will it not read anything because it's DC?
Why DC is not? Isn't there a flux here?
No.
Isn't there a flux in the core?
Doesn't even alternate.
There is flux in the core, but it is not changing. And according to Faraday's law, E is minus d phi over dt. So there is no flux change. There is flux, but there is no flux change. So according to Faraday's law, unless there is a change of flux, you won't have an EMF. So nothing is here. That was what Faraday did, and he failed, right? And then he removed the battery, and then he saw some deflection there. So the EMF that is induced here will be present only if there is a changing flux. If there is no changing flux, there is no EMF induced. Now, suppose I disconnect this battery. Watch what happens when I disconnect the battery. When I disconnect the battery, the flux which used to be here suddenly goes away. Suddenly. It was there, and I'm disconnecting it. When I disconnect it, it is just gone. Time? Very small. In hardly any time, it's gone. So the rate of change of flux is going to be pretty high. And that will cause a big EMF, maybe in the thousands over here. And that is what I use to shock you all. Remember the shock that you used to get with that? Right? So when you were holding this, basically you're touching these two wires. That's what you're doing. You're holding this. And what I was doing to this, I was connecting just a 1.5 volt dry cell. If you remember it right, when I connected it, you won't feel a thing. But only when I disconnect it, you feel it, right? What is the difference between connection and disconnection? When I connected it, the current here is kind of getting established. Make sense? It's getting established. It is not able to suddenly go to the highest value of 1 or 2 amperes. So there is definitely an opposition. Thank you. There is definitely an opposition. And because of the opposition, the current here does not grow all of a sudden like that. Instead, it grows like this. It takes a long time. So when I connect it, you don't feel anything at all because the time taken to establish that current, the time taken to change that flux is a big value. So how many volts EMF can you expect to get over here? Probably something less than 5 volts. That's the reason why, although you're holding it and I'm connecting this cell, you will still not feel a thing. But the moment I disconnect, what is happening is, in a very, very, very short time, the current in this wire suddenly becomes zero, which means the flux that was passing through this core suddenly drops to zero. Because if there's no current, how can you have a magnetic field? You see? There's no current, there's no magnetic field. And so as soon as the current drops to zero abruptly, the magnetic field also drops to zero abruptly. That makes the change of flux over time high, momentarily can reach thousands. And that's what actually you are holding on to. And the 1,000-volt pulse is what creates that miniature current in your fingers, right? So what do you understand is that, there's a saying that the EMF at make is much smaller than the EMF at break. It is something that is commonly said in physics, especially in a transformer or any induction device. The EMF at make, which means when you make the circuit, the EMF induced is much smaller compared to the EMF at break. Because when you break the circuit, the change of flux is going to be, the rate of change of flux is very high, so the EMF will be much higher. Make sense or not? So, yeah, so if you have a DC connected to a transformer, you will not get anything at all. Yes, you will have flux and all that here, but there won't be any EMF induced. And when will EMF be induced? Only when you disconnect it or connect it. But when you disconnect it, you will get a bigger EMF for the reasons I just said. And so a transformer is usually, not usually, always, used only with AC, alternating currents. It's fluctuating. So that one is 110, so 110 or 120 volts at 60 hertz. So it's fluctuating at 120 volts, 60 hertz, up and down. So this current is alternating, so the flux is alternating back and forth, and so this will experience change of flux, alternating, and so you'll get alternating EMF induced here. So the output is going to be alternating as well. At what frequency? 60 hertz. But the voltage here depends on multiple factors. The voltage there depends on multiple factors. Now let's look at a real transformer, something like that. That is, you can see there are so many legs here. Why there are so many legs is because there are multiple transformations taking place in here. Multiple, not like this, just 2 and 2. Not an input and an output. There are multiple inputs. You can see the corresponding wires going all the way up, and there are multiple outputs. So this probably is from television. So this could be the culprit, possibly. We don't know. So, but this is a transformer. I'll just pass it around, and I'm going to draw this right now. Okay. So the real transformers, they look more like this. Yep. Now the windings. This is the place where the windings are actually done. So the windings go like that. This is called the primary winding, and it's wound on this core in the center. So what happens is the magnetic flux that is produced from here can loop like that, like convection. Make sense? So it's like convection. And where's the secondary? The secondary is right here. That's a secondary. It's wound at the same spot. So primary and then the secondary, they go together. Sometimes the primary is on one side and the secondary is right adjacent to it. So the windings are done in different ways. You can just pass this through. And the core is magnetized. Laminated. The core is laminated. I'm getting the word magnetized from Nick. All right. So the core is laminated. Make sense? The core is split into multiple sheets. If you want to have a look at it once again, this one. Did I pass this? No. Look. Did I pass it?
Not today. You did.
Okay. So you can closely look at it. This is what you see. And these are sheets of the core, split into fine sheets, and those sheets are dipped into varnish, and the varnish dipped sheets are non-conducting to each other, and they stack them together and pack it properly. I think they have even welded one of the sides, so to make sure that it is not going to vibrate. You don't want it to be loosely packed, because if it's loosely packed, what will happen is when the magnetic flux is kind of changing, those metal sheets will start chattering. They'll start vibrating. You know, when I was turning that thing on, it made a lot of noise, right? The main reason is because the windings and the core, they're all like loose. I mean, not too tight. That's the reason why it was making a lot of vibration sounds. And that, in a transformer, these are very, very highly compacted and fixed. So when you operate this transformer, you don't want these things vibrating. Otherwise it causes a humming sound. You must have heard these humming sounds when you pass next to transformers. When you know, like on the streets, you do see some transformers. As you walk by them, there'll be humming sound. Sound is basically coming from sort of vibrations that are magnetically produced. Sometimes as you walk next to a tube light, you know, you hear the humming sound. There will be a big difference between like when that tube is turned on and turned off. Because one of the components that are needed for this tube to work properly is called a choke, which is basically a coil. And that is what, if it is not properly manufactured, it can cause humming sounds. If it is well made, none of them causes sound here. But there is a choke behind each. It's behind the frame. It's just a little box. And what's inside the box is iron. It's basically like a transformer, but it's not like, it is only like a wire that's going around, just like a solenoid. Just like a solenoid, that's it. That is called an inductor, and that is a choke. And if that is not well made, or if it is not properly compacted, if you give room for vibrations, it will vibrate. Okay, so that's why you hear the humming sound. So if you hear the humming sound from a tube light and all that, understand that the choke is not. It is functioning fine. It is the culprit. So change the choke, and then you'll be all right. No one wants that. All right. So coming back to the transformer once again, what are you connecting to the primary is our supply of 120 volts AC. You have AC connected there. Okay? Now when I connect an AC here, now kind of pay attention here. When I connect AC of how many volts? 120 volts. That AC is connected to a copper wire. Think of this. All you see here is a copper wire. And the copper wire is back here. How much will be an approximate resistance for a copper wire? Even if you have a lot of turns, it's copper. So maximum 1 or 2 ohms, maximum, right? If the resistance of this copper wire is 1 or 2 ohms and you connect 120 volts to it, how many amps do you expect? 60 amperes. 120 is the voltage and resistance is like 2 ohms max. So you can expect 60 amperes in this wire, which is not what happens. Why? Why? You connect 120 to something that's got only 2 ohms, and then you're not getting 60 but hardly any current. The reason for that is induced EMF. It's induced EMF again. Now this is called self-induction. Self-induced EMF. Okay. Self-induced EMF, what does that mean? You're connecting this, right? What is this going to produce? Changing flux. Okay, so there is a changing flux in the core. Produced by what? Produced by this, your supply. And this changing flux is experienced by itself. Isn't the primary a coil also? Right? The primary itself is a coil. And so when the change of flux takes place in itself, according to Faraday's law, it will induce an EMF. It's called the back EMF, and the induced EMF, let me call it EP as the induced EMF, and that's minus d phi over dt. This is called the back EMF. Back EMF meaning it is against what you supply. You get it? Or it is highlighting Lenz's law. It's highlighting Lenz's law, the minus sign. The minus sign, back EMF. Which means what? Which means the back EMF that is produced by this coil, and that process is called self-induction. Self-induction. Induced within itself. Like for example, one of you do a test and you are very pleased with the outcome. And so you get self-motivated, right? For the next test you feel like, I could do it. Let me go for more. Let me do it better. You are doing something and you get more self-motivated. That's like self-induction. Self-induction is when something is happening in the primary, the same primary is subjected to changes of flux, and therefore the same primary will produce this back EMF, which is going to be nearly 120. So if you supply 120, you can get 119.99 return. You can almost get all of it back as back EMF, especially when you don't connect this to anything else. If you don't connect this to anything else, it's just left open. You're sending something and you get back, no gain, no loss sort of thing. Now why 119.999? Because there is some loss here still. It could be eddy current loss, right? Or heating loss in the wires, magnetic losses, although we have tried to prevent it, but still some magnetic leakages can still be there. So you won't get 100% return, but you will get very, very close to what you supply. Now, you're putting in 120 and you're getting back almost 120, like 119.99. So what's the net voltage? It's like 0.01. The net voltage, because it's a back EMF, it's like going to be opposite, right? So the net voltage is going to be like hardly there, 0.01 or something. So the current over here, which we will call as IP, is going to be hardly there. Make sense? You get this point? The current will hardly be present because the supplied voltage and the back EMF kind of cancel off. So IP will hardly be there. Also, this is alternating. That's why I'm not putting any arrows. I can't put arrows over here because it's not direct. So when I write IP there, understand it is an alternating, there's no arrow indicating, right? So the primary is getting power, and then whatever power it is almost returned. That's why when you have a transformer or an adapter plugged in and you're not using it for anything else, you can leave it there. It won't cost you a thing. Why? How is it that you're not, spending any money even though it is plugged in? Is because yes, you're plugged in, 120 is going in, and literally 120 is returned in the form of back EMF. Make sense? Now, when is it possible that you will pay for it? Is when you have a bad transformer or a poor transformer. When you don't have a proper transformer, it won't give you back what you gave to it. And where is the rest going to go? Heat. So if you plug in an adapter and if it is heating up unnecessarily, that is not right. But if you're connecting this to something and if it's doing some hard work on this side, then it will heat up. Say Mac chargers. Do you think it is heating up sometimes? Yeah. If you're putting it to work, it'll start heating up. Otherwise, if it's already charged and is fully charged, then you'll see it's not doing anything. Yeah. So IP is the primary current produced by what? Self-induction. Now, self-induction and mutual induction is one area we don't really go into numerically, but that is something that you will learn when you're in college if you're taking physics, surely. The first things that you will actually end up doing in electromagnetism is self-induction and mutual induction. So now what is mutual induction? Mutual induction is something happening in the primary induces an EMF in the neighboring coil, which is the secondary. So ES is minus d phi over phi s, phi p, phi s over dt. How did this EMF come into existence? This EMF came into existence because the secondary is a different wire, right? So if the primary can have a back EMF, can't the secondary also have a back EMF? And that's what it gets. Well, this is the back EMF, but that is the only EMF in the secondary. It's not opposing anything. That is what is available right there. And this is caused by mutual induction. Mutual induction means if something is happening to one and the other will start doing better. Right? So if Adam is starting to get good scores, Kristen will be motivated to learn and he will start doing better too.
Yes.
So that's called mutual. That's called mutual induction. Mutual induction. Something happening here promotes him also, or makes him also do work. Get it? That's mutual induction. Self-induction is he does good, he is self-motivated to do better. That is mutual self-induction. So in a transformer, both are there. How the primary is getting this kickback is actually because of self-induction. How is the secondary getting its EMF? Is because of the same effect, mutual induction. Whatever is happening here causes an effect on this side. That's called mutual induction. Now, phi p. So EP. So EP is equal to minus D. What is phi made up of? What's the formula for phi? It's a magnetic field. BA N. Yeah, those things are there, but I'm not including them because they're not at an angle. They're perpendicular, right? So I'm not using anything else. I'm just using B straight away. We are not interested in that. Other factors over dt. Now area and the magnetic field, they're common for both wires. Do you see it? Magnetic field and area are just constants for this transformer. But this is different. The number of turns in the primary it depends. So this equation becomes minus BA. No. I'll take the constants out. So A and P dB over dt. You know, when you differentiate, you can take the constants out. It is the flux, it's a field that is changing. Area doesn't change, number of turns doesn't change. The same way, EMF induced in the secondary is minus d BA NS. So NS is the number of turns in the secondary, NP is the number of turns in the primary.
Where did the minus sign go? Or the negative sign?
Oh, minus over dt, and which again becomes minus ANS dB over dt. Now if I divide both these equations 1 and 2, if I divide both these equations, see this, EP over ES, if I divide both these equations, minus and minus are gone, area gone, dB over dt and dB over dt is gone because they both share the same changing flux. Get it? Same changing field. But since the number of turns are different, they will stay out. Now, since EP, which is actually the back EMF in the primary, isn't that basically what you supply? Primary voltage? So the primary voltage that you're supplying, the voltage supplied, since EP is approximately equal to voltage supplied, we can use the voltage supplied as this. Okay? So the voltage supplied to the primary, I'll call it VP now. Voltage supplied to the primary over EMF induced in the secondary. Some books call it VS, voltage in the secondary. Instead of using the term EMF, they just say how much is the voltage in the secondary. Is equal to NP over NS. That's an important equation for a transformer. This is the ratio of voltages is equal to ratio of turns. The ratio of voltages will be equal to the ratio of turns, number of turns. So in a transformer, VP is what you supply on this side. VS is what you come out in the secondary as output. This is voltage input, voltage output. You'll see some books saying V in, V out. It's the same thing. You get it? V in into the transformer, V out of the transformer. So V out is always the secondary. V in is always, so transformers are made for a specific purpose that way. Now can we use the transformer the other way around? Can I make this a primary and make that a secondary? Yes, you can. But it is designed to work well in one manner, so the other way around it may not be that efficient, but it will still work. Both ways it should work. Okay? So this is an equation that you can understand. All right, now next thing, studying that equation better. If NS is less than NP, then VS is less than VP. The voltage in the secondary is less than the voltage in the primary. And this kind of a transformer is called a step down transformer. Anyone to tell me why it's called step down? Step down. Less voltage. to charge your cell phones, you need only 3.6 volts. But what's coming out from there is 120.
Step down.
So step down. Okay? So you step it down, and then you can use it for your purpose. So transformers, most transformers are actually the step down types because we use them for adapters, and AC is the most convenient way of transferring energy from one place to another place, or transforming energy. AC, alternating currents. Nothing better than that. That's why you have all the wires that are taking energy, electrical energy. That's the best form of energy that can be transported. Nothing better. DC? No. Well, DC can go, but DC suffers from other issues. That is, okay, if you have a DC, how can I use that DC and run, how can I charge my cell phone? It's 120. Because transformers don't work on DC. You understand? Transformers, so step down, step up actions cannot take place with DC. So we need instruments called inverters. You know what an inverter is?
Just makes it into an AC.
Yeah, makes it into an AC, exactly. So you get inverters. I think you can buy inverters for your car. I have one in my car. So what you do is you're plugging it into your cigarette lighter. So 12 volts DC gets in. And what it does is there's a circuitry which makes the 12 volt DC into 12 volts AC. Make sense? And then comes the transformer. And that transformer is step up. How many times? 10 times. So once you change the AC into DC, and then now a transformer will work fine. And the output of the transformer is going to be 120 AC. So I can charge my laptops and all that on the go. You understand what I'm saying? I've charged my Mac and all that on the go. When we are driving long distance, especially the last trip, last June. Not last June, last June. Alaska. I think I told you all. Totally 6,500 miles driving. It was good. So this charger was really helpful. This thing was really helpful because all the laptops and all that, charging the laptops was very conveniently done. It's also got USB outputs. It's only like $20, $25. It's a small box. Plug it in and you have all the outlets. But again, limitations are there. You can't take too much power from there. If you really want to take too much power, then hook it up straight to your battery, not through the cigarette lighter. Then yes, you can. There is a certain power specification on the inverter that you can actually use. 87 or something. There's a time again when I made my inverter, my first inverter. Well, I never heard about inverters till then, which turned it off.